Hey guys, so some of you have been asking about this question, and it is a little bit fiddly, and I just wanted to go through it a little bit, give you guys a little bit of a hint to help you out. So the question has actually got two parts to it. The first part to it is if you started with a radio-labeled bicarbonate molecule, so here's the carbon-14, and it's radio-labeled, it's passing through gluconeogenesis, so it's going to be synthesizing glucose at the end. Use an asterisk to indicate the location of the carbon-14 in all of the intermediates until you get to the glucose at the end. And so immediately, you're going to want to take the asterisk and you're going to want to drag it here because you need to indicate that this is the labeled carbon. We know it is. It says 14 carbon-14 bicarbonate. That's the only carbon, and it's even labeled for 14C. So we can drag this asterisk and move it there. After that, we're going to drag asterisks to the appropriate place on the other molecules to indicate where this carbon-14 is in all of the molecules. And we're going to do something similar here with go through gluconeogenesis starting from pyruvate. So a bicarbonate, we go bicarbonate and integrating into oxaloacetate, PEP, and then moving through all of the steps to get glucose. Here it's pyruvate through to oxaloacetate, and then down through the intermediates until glucose again. With the other pyruvate one, there's two ways to know where you start, because with bicarbonate, you've only got one carbon, so it must be, that carbon. With the pyruvate, it says that it's 1,14C pyruvate, which means that carbon 1 of pyruvate is labeled. And so we label organic molecules like this, starting from the carboxylic acid, which is carbon 1, 2, 3. So it knows this carbon, but also they've already labeled it with a 14. You can go ahead and drag that across there. And then, so if we start with the bicarbonate, we go to our lecture on the TCA cycle. If we follow up to slide 37, it covers, or 35, 55, 56, 57. It covers this molecule, pyruvate carboxylase, this protein, this enzyme. And what pyruvate carboxylase does is that it generates oxaloacetate in an anaplerotic reaction from pyruvate by putting a bicarbonate, a CO2 from bicarbonate to extend the carbon chain from 3 in pyruvate to 4 for oxaloacetate. And if we follow through this mechanism, where it becomes important is down. This first bit really is just preparing and getting it ready and illustrating the flexibility of the biotin cofactor that's helping out here. But if we look here, this is where it starts to get a little bit more relevant, is that you've prepared you've got the bicarbonate, you've added CO2 to the biotin, and now you've got that biotin, you've got that CO2 primed and ready to add on to the pyruvate. And here we have the pyruvate molecule here. And you can see that you have the carboxylic acid end, you have the ketone here. So this is a keto acid end. So it's carbon 1, 2, 3. There's the carboxylic acid there. There's the ketone group, and there's the CH2 at the end, or the methyl group at the end. One of the things that happens is that this rearranges to form the enol form. So from the keto form, which is the keto form, is going to be CO. The enol form is going to be C double bond CO minus. So it's going to the double bond is moving to here instead, and that's what we have down here. And then that carbon 1, 2, 3 is going to be the double bond, the electrons in the double bond are going to attack the carbon of the CO2 and join it onto the end to make oxaloacetate. So the top half of the molecule is actually just pyruvate with a CO2 added onto the bottom. And it's carbon 1, 2, 3, 4. And at one end, you have the keto acid. And at the other end, you have the just the carboxylic acid on its own. It doesn't have a ketone next to it. And so that's where the CO2 from the bicarbonate gets added. You see it's red, and it's red. It is carbon number 4, the furthest away from the keto acid group. And you can see it a little bit as well on the gluconeogenesis slide. If I clear this off, where this is gluconeogenesis, and it's talking about the first bypass, and it's kind of part A and part B. And part A is, I actually don't show the mechanism of part A, but it's the same pyruvate PC, pyruvate carboxylase that I was showing here. It's the same thing from the TCA cycle slide. In the gluconeogenesis slides, I don't show the mechanism this time, but you can actually kind of see it in the part 1B, which was the PEP carboxykinase. You can see that it's the same thing, where we have the carbon 1, 2, 3, 4, and here's the keto acid group, and the carbon furthest away is what was added on as the CO2. And in part 2 of step 1B, part 2 of bypass 1, you see that carbon number 4, the CO2, leaves to leave you with PEP, and that's what you've generated. Carbon 1, 2, 3, and the ketone has been is now instead the ketone from oxaloacetate. This one here is now this here, the phosphate group that's been phosphorylated as the ketone. So we can see that the CO2 that you add on to pyruvate to make oxaloacetate is at the 4 position, and then it leaves and it is no longer present. That's the key thing. The CO2 goes on the end furthest from the keto acid group and then leaves when you generate PEP. And if we look at the question, I'll clear those drawings away again. So here's the carbon, and so it's this is and here's the CO2. It's going to add on to the end furthest away from the keto acid. There's the keto acid. So it's 1, 2, 3. It is carbon 4, and then in the next step, step 1B. That carboxykinase, PEP carboxykinase enzyme. 1, 2, 3. Carbon 4 is lost as CO2, and the ketone group now a phosphor group. And then you can follow that through to the end to say, well, to say where the asterisk is, if it is there at all. Follow that through to the end. Similarly, with pyruvate, if you were to start with carbon 1, 2, 3, now, because this is the keto acid, so it's down here, it's down here. If you were to have this one as the start, you follow it through. You can follow that through to the end, and it will get interesting when you get to here. This bit you're going to get fiddly. This bit here is going to be fiddly. But if you track where that star is on these molecules, and then remember it's you're generating glyceraldehyde 3-phosphate and the D hat, and you're going to do whereas in glycolysis you do the retroaldol condensation. This time you're actually going to do an aldol condensation because you are doing the you're putting them together because it's gluconeogenesis to make glucose. So if you look at where the star is on here and the star is on here, then it's going to tell you about where it is on here. And you can look at it as if this is a phosphate, and this is a phosphate, this is a phosphate, and this is a phosphate. So it's kind of going to be like 1, 2, 3, 1, 2, 3, which means it's going to be 3, 2, 1, 1, 2, 3, because they condense here. And then where that is going to be in turn on the glucose molecule. You can answer that one as well. Just by going through reversing the steps of gluconeogenesis from the making the pyruvates or oxaloacetate. So it's actually the same as this one up here, except it's saying labeling carbon 1, and this time it's labeling carbon 4. So you can just follow it through and look at the differences between them. But that should give you the information you need to figure this out. If you need any more help, or you want me to run through it in a different way or talk it through, then please feel free to email me. The homework is due tonight, and have a good day.